Level 25. Let's go. Let me drag this all the way over, and we're going to talk to Simplicio and Socrates. All right. This is the last one. Socrates. Yes, it is. Okay, quick question. So we were talking last time about indexing. I thought that was I have to get to this topic at some point in a real analysis course. You leave real analysis without knowing about countability and uncountability, then your professor should be, publicly shamed, tarred and feathered, whatever. So Simplicio says, how come we need general indexing types? When we were talking about compactness, we had these types, iota. Iota was this arbitrary type. What can't I just, index by the natural numbers? Can't I index everything that I want to index by the natural numbers? So Socrates says, great question. Besides the generality of that abstract indexing types provide, there's a crucially important difference, and the answer is no. So there are some things that it's not possible to index by the natural numbers. Really like what, says Simplicio. All right, so Socrates starts telling him a story. So Professor David Hilbert, famous mathematician, liked to tell a story of a magical hotel. So this hotel, so here's the hotel. Okay, and it has all these rooms. So there's room R1, room R2, room R3, and so on forever. And the hotel has no vacancy. It's the first night. The hotel is completely full. Guest 1 is in room 1, guest 2 is in room 2, guest 3 is in room 3, and so on. And so, infinity is equal to infinity. Every single room is taken, and every guest has exactly one room. We're not asking people to bunk. They don't, these are strangers. That's not what you do. So Simplicio says, so far so good. Simplicio says, I mean, yeah, but you're talking about infinite hotels and infinitely many people. There's only, 8 billion people in the world. Come on, let's just go with me. New person shows up. So guest G0 shows up and wants a place to stay. And their clerk says, hey, can't you read? It says no vacancy out front. Sorry, we don't have room for you. Professor Hilbert's around the corner in his office. He overhears and comes to the front desk and says, sorry, sir, come on back. We'll find a place for you to stay. And the clerk says, but, you're going to send him to the back somehow? Like, what are you going to do with this guy? Every room is taken. There's no such thing as sending him to the back. You can't send it to the end of infinity. And Hilbert replies, you're absolutely right. There's no such thing as sending him to the back of infinity. I have to, that's not a room assignment. Every single person, there's a ledger, right? This is what the ledger looks like. And room 1 has guest 1, and room 2 has guest 2, and so on. Everybody's name goes in the ledger, and that's the only way you assign rooms. You don't say G0, go to the end. There is no end. Does that make sense? But he gets on the loudspeaker and says, okay, can the guest in room 3 go to room 4, and the guest in room 2 go to room 3, and the guest in room 1 go to room 2? I'm just going to slide everybody down one and give them a minute to pack their things and move. And then he turns to the guest and says, in just a moment, room 1 will be available. Feel free to take that one for the night. Okay? Does that make sense? So Simplicio says, oh, that's pretty cool. So if you take infinity, there's infinitely many guests, and then you add one more guest, you can still fit that in infinitely many rooms. Pretty cool. Socrates says, you ain't seen nothing yet, kid. On the second night, so this is night 1. Night 2. On the second night, again, the rooms are all occupied, R1, R2, and so on, occupied with guest 1, guest 2, and so on. Simplicio says, oh, so guest 0 left, and everybody had to move back again. I don't think I'd like to stay at this hotel. Okay, whatever. Shush. On the second night, a car pulls up with 10 people in it. What does the clerk do? Hey, everybody, go down 10 rooms. So the guest in room N goes to room N plus 10. And now I've got 10 rooms available. No problem. Yep, let's do it. On the third night, a bus arrives. So this is night 3. On the third night, a bus arrives. So here's the hotel, room 1, room 2, room 3, and so on. There's guests everywhere. Guest 1, guest 2, guest 3. And now we have a bus. This is the bus. And the bus has passenger 1, passenger 2, passenger 3, and so on forever. So by the way, this On night 2, we learned that if infinity plus 1 is the same thing as infinity, of course, infinity plus 10 is the same thing as infinity. No problem. On night 3, the bus arrives and has infinitely many passengers on it and wants a place to stay. And the clerk says, if the hotel was empty, I could put you up. If there were 10 of you or a million of you, I could put you. Okay, so we talked about room. We talked about whatever night that was, night 3, infinity plus infinity. Then we talked about night 4, infinity times infinity. Here comes the ABBA bus on the 6th night. And so there was a night 4, a night 5, and now we're on night 6. Night 5 was infinity times infinity, is just as large as infinity. Night 4 was 10 times infinity, is the same size as infinity. And night 5, or night 6 rather, is now this ABBA bus. Okay, so the ABBA bus, the Swedish bus, party bus shows up, and Hilbert says, so the clerk says, I think we can seat you. Hilbert says, it's not possible. The clerk says, what do you mean? We've done all kinds of other things. And Hilbert says, take out the ledger. So here's the ledger. Person in room 1, person in room 2, person in room 3, and so on. This is some ABBA. This is some BBAAA. This is some ABBAA. Okay. And he says, as we just discussed, imagine that there's one person that we haven't placed on the roster. That's a contradiction of the assumption that we've filled the hotel with everyone on the bus. And so not housed is the person whose first letter disagrees with the person in room 1, whose second letter disagrees with the person who's housed in room 2, whose third letter disagrees with the person in room 3, and so on. That's going to be an infinite sequence. This is the original Cantor diagonalization argument. Okay. So that's the argument. So you're going to change the name of the person in the nth room at the nth letter, and that will give you the name of somebody who's not anywhere. Okay. How big is this infinity? So Simplicio says, we saw infinity times infinity was okay. How big is this infinity? Right. Everybody sees it as 2 to the n. So if you think about if it was only length 4 names in A's and B's, the first letter can be an A or B, the second letter can be an A or B. So for length 4, A, B, B, A, there's 2 to the 4 names. And so this big bus, the party bus, the bus has 2 to the infinity names, people. And 2 to the infinity is strictly larger than the infinity of the hotel. Okay. So that's the Cantor diagonalization argument. It shows us that there are different sizes of infinity. And what does this have to do with indexing? Which is how we got here. Why do we want to index over arbitrary types and not just over the naturals? Well, on the first night, all we did is re-index the naturals. N goes to n plus 1. On the second night, we indexed all the integers. How did we index the integers? How are you going to make a 1-to-1 correspondence between the integers and the naturals? Switch between positives and negatives, right? So 0 stays at 0. Then maybe we put the odd rooms have the naturals in them. And now we've made room for the even rooms to have the negative naturals in them, in their order. What was the 5th night? The 5th night was infinity times infinity. That was a counting of, Jeffrey, the rationals. The rationals are P over Q. P is an integer, Q is an integer. That's infinity many numerators, infinitely many denominators. So all you're doing is putting all of the possible numbers with denominator Q on one bus. And then arranging the numerators. So Q is the bus number. And you'll have some redundancy here. So if you've already placed 2/4 when you place 1/2, so don't bother to just skip that one. So again, it's easy to keep track of this. So the rationals, even though the rationals are dense inside the real numbers, can still be counted, can still be ordered. So there exists a one-to-one onto map. We've talked about one-to-one maps, injective maps, and surjective maps. So there exists one-to-one and onto a bijective map from the naturals to the rationals, to every single rational. That's infinity times infinity. Okay. So then we had infinitely many buses with infinitely many passengers. We can think of the buses as denominators, the passengers as the numerators. We've indexed the rationals. So what about the 690? What was that ababus? So let's think about the real numbers. In fact, not all real numbers. Let's just think about the real numbers between 0 and 1. In fact, not all the real numbers between 0 and 1, but just the set of numbers between 0 and 1 that have a decimal expansion that only uses zeros and ones. Okay, so here's ABBA. That small collection of real numbers is already uncountable. And hence the interval 0, 1 is uncountable, and hence the real numbers are uncountable. So these infinities are uncountable. These infinities in infinities. This is not a course in logic and cardinality and so on. Infinities are uncountable. That's the term for things that do not have a one-to-one onto bijection to the naturals. Okay. Right. You can watch a Veritasium video about this. So question? No. So if 2 to the infinity is strictly larger than infinity, Simplicio really is asking for it here. So if you have 2 to the infinity, and that's strictly larger than infinity, is there some, is it like the next largest? Is there something in between? Anybody know? Daniel?
Either one of that.
Yes. So that's the continuum hypothesis. It depends on what the definition of is, for those of you who remember that old phrase. Okay. Never mind, we're not going to talk about that. All I want you to understand for now is that there are surprisingly many things that we can index by n, by the naturals, and also lots of these are called the countables, and there are also things that we can't index by n. And so that's why it's actually very important that we have abstract types in order to index things. I mean, among other reasons why countability and uncountability is an important topic in mathematics. Okay? All right. So what's today's lesson? What are we actually supposed to learn today? Okay. I still owe you a justification from lecture 2 about Newton. And the thing that Newton did to compute pi was, so back to Newton. This is our last chance. What is going on? No, I just have to get rid of this, right? This is in our way. This is in our way. Okay. Back to Newton. If you recall, Newton was trying to compute the integral of 1 minus square root of 2 when he was evaluating pi. He had found the Newton binomial series, which is this expansion, whatever it is, x to the 4th over 8 and x to the 6th over 16 and 5x to the 8th over 128 and so on. Okay, there was this series expansion. And then Newton went to integrate this from 0 to like a half dx. And he did it term by term. And the question is, are you allowed to do that? Can you integrate term by term? What are the conditions under which you can integrate term by term? Okay, so in other words, if you think of like a sequence of functions, so f0 of x is 1, and f1 of x is 1 minus x squared over 2, and f2 of x is 1 minus x squared over 2 minus x to the 4th over 8, and so on. Okay, so we have a sequence of functions. For any one of those functions, we know that the integral is linear. And so the integral of f7 is the integral of 1 minus the integral of x squared over 2 minus the integral of x to the 4th over 8, and so on, up to whatever the, let's see, 0, 1, 2, 3, 4. So the integral of f4 goes up to the integral of 5x to the 8 over 128. and stops there. So the fact that this integral can be turned into this finite sum of integrals, no problem. That's just linearity. Can we continue this series indefinitely? And will it recover this integral? So main question is when is, so given a sequence of functions, converging pointwise to some capital F, when is capital F integrable? So when is, I guess I should say capital F integrable? And if it's integrable, when is the integral equal to the limit of the integrals of the fn's? Does that make sense? That is what will justify, finally, this thing that I promised on lecture 2 about Newton's computation of pi. So, Simplicio says, let me think. Okay, so first of all, each of the fn's had better be integrable, or else I can't even write, this isn't a real number. Fine. Simplicio is guessing that Socrates is about to tell him a whole slew of examples where pointwise convergence is not enough. And Socrates says, you know me very well. Okay, so here's one counterexample. So example 1. Think of the functions that are 0 until you get to n, and between n and n plus 1, they jump up to 1. So it's 0. I don't care what happens at these points. This is my family Fn. What does Fn converge to pointwise? Sean. Exactly. The function that's identically 0, right? For any fixed x, pointwise, this is pointwise. You give me any value of x, once capital N gets past x, all the functions after that are 0. All the values of all the functions at this point are 0. So there's nothing to do. This little bump just flies off the end of the real line. What are the integrals of the fn's? 1, right? It's a square. The area under a square is 1. And of course, the integral under this big thing is 0. Okay, so that's bad. All right, maybe the reason this is bad is that we have sort of infinite amount of room to work. Maybe if we keep things into a compact interval. So maybe compactness is important. Okay, so Socrates explains this example. Simplicio says, okay, we're getting f of 0. We're getting the integral of capital F to be 0, which is, of course, not 1. So let's keep all the action in 0, 1. Let's stay in 0, 1. Anybody think of a family of functions that's going to have a problem in 0 to 1? How about we squeeze? I think Jeffrey was about to tell me something. How about we squeeze all of this escape of mass into that compact region by going from 0 to 1 over n, we jump to height n. So we're here, and then we're here. How about this family of functions, Fn? What's the integral of each of them? Oh, where do they go pointwise? Right? Everybody see that? It's for any x greater than 0, they definitely go to 0 because eventually x will be below 1 over n. The Archimedean property strikes again. And what about x equals 0? Well, for that one point, the limit blows up, but whatever. Make that one point equal to 0, or if the limit blows up, call the function 0, Joe. There's a version of the Dirac delta function that this approximates. Yes, this is like the Dirac delta function. Yeah. Well, if you were to integrate something against this thing, it would behave like it. So The delta function is not a function, it's a distribution, which means it doesn't exist as a function, but it does exist as something that you can integrate things against. That's 411, if not 501, a topic for slightly later. But you're absolutely right. This is exactly the kind of thing you do to get a Dirac delta. And you use that all over the place in analysis. So what's the integral of all of the fn's? Yeah, it's a rectangle of height n and width 1 over n. So this is n times 1 over n, which is 1. And of course, that's not equal to the integral of capital F, which is 0. Daniel. Yeah, what about continuity? Okay, so Socrates says, here's what you do. On each of these, you get 1, and on each of those, you get that. Okay, so those functions aren't continuous. Maybe that's the problem. So compactness didn't solve it. Maybe continuity will solve it. Maybe continuity and compactness is enough. What do you think? Joe says no. Why not, Joe? Exactly right. So let's go from, let's see, I want something that's, let's go from 0 to 1 over n to 2 over n, and something that has area 1 again. So the base is 2 over n, so let's have a height of n. So this will be n. And you can work out what this line is, and you can work out what that line is, and then you can go down to 0. So here's a nice family of functions. And if you don't like that there's a corner here, you can make it smooth. Then you're truly at a Dirac delta. This is much closer to what a Dirac delta is doing. You can make smooth versions of these. So here's my fn's. They're continuous. You can make them differentiable. You can make them twice differentiable. You can make them 1,000 times differentiable. Daniel. Okay. Hold that thought for 10 seconds and then ask that question again. All right, so the fn's converge again to 0. The integral of the fn's is the area of the triangle with base 1 over 2n. So it's a half times 2 over n and height n, aka 1. And 1 is not equal to 0. All right. So continuity doesn't do it. Compactness doesn't do it. What does do it? So here's the explanation of what this function is. You can write it down. I should have just drawn a picture. What's the condition that we need to make this work? Is it uniform convergence? So Simplicio says, what about uniform convergence? Okay. So let's think. Suppose f is integrable, fn is integrable, and fn converges pointwise to f, but not just pointwise, but uniformly. And let's think about the difference. So what's the difference in the, so let's write the Riemann sum of order. I'm going to try to keep this straight. I'm going to use capital M for Riemann sum, because there's two different things happening here. There's Riemann sums that are converging, and then there's functions that are converging to f. So let's think about the Riemann sum. Let's say we're on an interval a to b. Okay, we want to integrate over some interval a to b. The Riemann sum of order m of our fn. And how does that differ from the Riemann sum of order m on the interval a to b of capital F? So let's just write this out. This is what? B minus A over their m pieces in the subdivision. I mean, let's draw a picture. We should always draw pictures to explain things. So here's my fn, and it's going to closely approximate the limiting function capital F. And here's A, and here's B, and we're chopping this into m pieces. The width of each piece is B minus A over m. And then we're going to evaluate all of these rectangles on the right. The right Riemann integral is the only one that is allowed in this course. So it's the sum is I goes from 0 to big M minus 1 of Fn evaluated at a plus I plus 1 b minus a over m, that is the Riemann sum for f. And I'm going to subtract off the Riemann sum for capital F, which is exactly the same thing, evaluated at exactly the same points. Okay, so I can write this as f minus capital F evaluated at these same points. So what? John? That's the whole point. The uniformity, remember what uniform continuity says. For any epsilon, there exists a capital N, so that for all n, at least capital N, and for all values of x, no matter where you're evaluating these functions, they always stay in with utmost epsilon once the function is past little capital N, then no matter where you evaluate it, this is going to be less than epsilon. So all of these, as long as this mesh, sorry, not as long as this mesh, has nothing to do with the mesh. This is completely mesh agnostic. Just as long as, that's the whole point. Let me write it here. So for any n whatsoever, the entire story is independent of the mesh. All that matters is that fn minus f, as long as n is large enough, this distance is at most epsilon for your given epsilon. You give me an epsilon, I'll give you a capital N, so that you can, if you go down far enough, I like to think of functions, right? The fn's are converging down to f. If you go down far enough, then all of these differences, no matter where you evaluate them, are going to be at most epsilon. You'll add m of them. So what's this contribution at most? M epsilon divided by m. And the whole thing is at most epsilon times b minus a. So the Riemann sum of any order for this and the Riemann sum of any order of this differs by at most epsilon times b plus a, b minus a, as long as n is large enough. For little n large. I'll just say for little n going to infinity. Does that make sense? So that's what Simplicio is saying there. Cool. That means that we can simultaneously show that f is integrable by comparing its Riemann sums to those of fn for large n, and that the integrals of the fn's converge to the integral of f by the same kind of reasoning. So uniform convergence, not continuity, not compactness, just uniform convergence should do it all for us. And Socrates says, let's do it. Okay. Jump.
For X out of that.
This thing? Sorry. Is that better? Okay. Do you want to take 6 minutes, 6 or 7 minutes, and see if you can work out the proof? Should we make this a quiz? Let's make this a quiz. Try to get a proof of this fact all by yourself. I'll come around and pencil. Oh my goodness. I'm in the class unprepared.
Oh.
And I have a pen.
Well, it's not the Hilbert report. So, Professor, just to clarify, we're just proving that.
No, try to prove this theorem.
The upper bound.
No, try to prove the whole theorem.
Oh.
It's not a fair quiz. Just take a few minutes and actually think by yourself. See if you can, pretend this is the final exam. Could you prove this?
Can we, or can I get a statement of the whole theorem?
Yes. Let's get a restatement of the whole theorem. Here's a restatement of the whole theorem. So integrable of uniform convergence. So you have a sequence of functions fn converging to a function capital F. That convergence is uniform. You have two numbers a and b, a is less than b. I mean, we are integrating on a compact interval. We're assuming that the fn's have integral Ln. L is the limit. Let me write this down. So here's the theorem. We have a sequence of fn's. They're converging to capital F uniformly. And that's called H little f big F. Okay. We have some interval a to b. And we know that the fn's, this has integral, means that the integral of a to b from a to b of fn is equal to Ln. I'm just giving a name for the integrals. And that's it. And our goal is to show two things. There exists a capital F such that the L's, so that Ln goes to L, and the integral of f is equal to L. So I want to simultaneously show the integrability of f. There is an L so that the integral of f is L. The Riemann sums for f converge to L. And not just any L, but that L is the limit of the integrals of f itself. So this is the same thing as saying that the integral of the fn's converges to the integral of f. And capital F is integrable. There's no assumption on continuity. There's no assumption on anything other than uniform convergence. The fn's could be weird as long as they're integrable, and as long as they converge uniformly, capital F will be integrable. Take a few minutes and see if you can figure out why. Talk to one another. We discussed, the beef of the argument, but how do you make it precise? We talked. Work it out. Very easy to get this confused because you have two different kinds of things. The first thing I would do is draw a picture. I started the picture up there.
To come up with an L, or can we just use like LNs?
Why did the LNs have a limit? That's a big hint. Why is it a big hint?
I think the order of which you prove those two things matters. Like, if I need to prove that there is the limit in order to prove that has to.
But why was it a hint to say that you don't know that the LNs converge? What are you supposed to do? You don't know what the limit is. You don't know what the LNs supposed, where are you supposed to get this capital L? It doesn't say that the LNs converge. That's part of what you're trying to prove. You don't know where to go. You have to show that the LNs are Cauchy. I want you guys to like the synapses should say, what are the LNs? You know, the first thing I have to prove is that the LNs converge. What do they converge to? I don't know. Boom. If I don't know, then the answer is Cauchy. The way I'm going to prove convergence is to prove Cauchy. So how do you make the LN and LM close to each other when the L's are large?
Oh, because all the FNs converge, the uniformly converge to F, so you have to find the distance between FM to F, FN to F. So
Something like that.
triangle and flaw.
See if you can work it out.
Okay.
Should we work on it together, or you want some more time to think about it? Okay, a little more time.
When you're like comparing the two concepts, do you always assume the same connection?
It depends. Bless you. The way that we proved integrability when we had uniform continuity, when we said a function is uniformly continuous, therefore it's integrable, we had, again by Cauchy, we had to compare the Riemann sum at depth m to the Riemann sum at depth n. And do you remember how we compared those two? Exactly. We took a common refinement so that we can compare it at the same or similar points. Is that what we want to do here? Do we want to do something else here? I would draw a picture. Should I draw the picture for you, or do you guys, if you've drawn this one picture, then what are all these you see on YouTube, the clickbait videos? This one trick. What's the one trick that lets you pass real analysis? There is one picture that I always draw for myself. You guys want to see it, or do you have a picture on your page? Draw a picture on your page that you think is the picture I'm about to draw. Okay, so I have Ln, and I want to make it close to Lm. What's the only thing that I have to work with Ln? Exactly. The fact that the integral of the FNs go to Ln. Go to means if I take an order M Riemann sum, that'll be close. Okay, so bless you. For M large, the Riemann sum of order M of Fn will be close. This is for M as M goes to infinity, as M goes to infinity. So for large values of M, this is close to the integral, and the integral is Ln. And similarly, for large values of, maybe we can use the same M, maybe not. We'll see in a minute, bless you. For Fm, that also goes to this. This is supposed to be a capital M, and that's supposed to be a lowercase m. I'm going to try to do this for capital M. Is that better? Okay, so this is as capital M grows. Maybe, should I use a completely different letter, like a K or something? Yeah. Okay. You agree? As the depth of the partition gets large, both of these things go to their respective values. But how do I compare those two Riemann sums? Exactly. So I'm going to compare both of them to big F, right? The Riemann sum of big F. Does that make sense? So I can make this difference small on either end for any K, Remember this, the whole point was that this calculation we just did didn't matter how finely we refined the partition. It's just the uniformity that gets us a bound of epsilon times f. Why don't we write out what that theorem was? So we had a calculation. Let's do have the key identity is that you gave me the epsilon, and there exists a capital N, so that for all little n more than capital N, and for any partition, no matter how fine or not fine, bless you, I get that the Riemann sum of order k of Fn minus the Riemann sum of order k of big F is at most epsilon. That was the argument. Right? And again, it's just because, just to do it one more time, this is because this is the Riemann sum of order k of F minus F. And this is pointwise at most epsilon. And the Riemann sum, we can bring the absolute values inside, make this a little smaller, or make this a little larger. So I'm bringing the absolute values inside the summation. And these terms are at most epsilon by the uniform continuity. Actually, yeah, by the uniform continuity, I'll make them epsilon over b minus a, so that when I average and multiply by an extra b over a, this will be less than epsilon. I guess not less than equal to, just less than. Dane.
Would it be possible to do this, instead of comparing one to F, if you said, oh, well, the difference from V1 sum of FM or gives a V1 sum of F minus FM, that has plus epsilon, because if it merges to F, then they see again.
Sure. Yeah. Yeah. The fact that they converge to F means that the sequences are Cauchy. Yeah. But we need more than that. The fact that they converge to F pointwise means that they're Cauchy pointwise. What we need is a uniform Cauchy, and we have a uniform Cauchy, which I'm doing here by comparing it to F, to capital F. Yeah. So uniform convergence means they're uniformly Cauchy with respect to one another. But again, we're sort of proving that in the process of proving the theorem that we want. Does that make sense? So let's just state this. So have key. Yes.
Is that a picture?
This is the picture. This here is the key picture, the diagram. I want to get Ln close to Lm, and I'll do it by getting Ln close to the order k distance between Fn, the order k integral for large K. I'll get these two close for N large. I'll get these two close for M large. And then again, the fact that this is order K will tell me how fine, how large a refinement to do for these to be close.
How often do you draw this kind of diagram?
Every single time I want to do something.
Workhorse.
That's my workhorse. And we'll get to do it again when we prove the second part that F has an integral. How many changes will I need to go from Lm all the way to Lm? Yeah, 1, 2, 3, 4. So what will I bound each of these things by? Epsilon over 4. Okay. So here's the key thing. The key thing is that for all epsilon positive, there exists a capital N, so that for all little n, at least capital N, and for all depth of partition, the absolute value of the Riemann sum, I think it's the function, then the A and the B, and then the K. Hopefully that's right, minus, but the function is not F, it's Fn, minus the Riemann sum of capital F, A, B, K, is less than epsilon. I'm just going to sorry that out for a minute. Is that right? Yeah, that's right. Okay. You follow that inequality? We can fill it in later if need be. So let's prove that the LNs are Cauchy. So have is cow L is Cauchy L by, can I do this? No, but I can if I go into editor mode. So I'm going to cheat. Okay. So now we're in editor mode, and we're saying, why is it Cauchy? So give me the epsilon, and give me the fact that epsilon is positive. And I need to give you a capital N so large that as long as N and M are large enough, then this difference is less than epsilon. How large an M do I need to give? Brandon?
Is it the M from like uniform?
It's the M from uniform convergence with an epsilon over 4. Okay, so choose capital N, HN using what? Using HF capital F with epsilon replaced by epsilon over 4 and by bound. By bound. Let's see, did that do it? Beautiful. Okay. So now I know that the FNs differ by that much. I'll apply, let's see. Well, I guess all I really want is this key. I really want just these Riemann sums to differ by epsilon. So I've already used Fn inside the proof of key. So actually all I want is using key with epsilon over 4. Okay, these Riemann sums are within epsilon over 4 of each other. 1 for going from n and one for going to m. Okay, and then use that n, and give me the n, the hn, the m, and the hmn. So now our goal is still that lm minus ln is less than epsilon with these n's and m's. And I know that for any n, these Riemann sums differ by that much. So let's do another thing, which is let's get a k large enough that this distance is less than epsilon over 4. Where is that going to come from? HF int. Okay, so let me say specialize HF int to little n. Let's do it on this side, little n. Why is little n greater than epsilon, greater than capital N? I think I see it already, but I'll just say by bound. And then what is our A? A is epsilon over 4. So epsilon over 4. Aha. So this wants show 0 is less than epsilon over 4 by bound. Oh, it didn't do the first bound? Hang on. What's HF int? HF int is that for all n, where is HF int? Yeah, I'm going to. I was just going to. Okay, let's say choose K, HK using this. Now, all right, what's the problem? So K isn't going to be right yet. K is going to be some weird thing. Yeah, K is a function from the positivity of epsilon. So the positivity of epsilon is I want epsilon over 4. Show 0 is less than epsilon over 4 by bound. Oh, come on, by sorry. No. No. Really? Epsilon over 4 is greater than 0? That's what you're complaining about? Let's see. Epsilon over 4 is greater than 0? You don't mean A. I think A is a dummy variable. Well, so let's see. I just want to see what, let's do have colon equals F, HF int N. Okay, so what is that? That's has integral. Has integral is that this thing, the limit of this sequence of Riemann sums is ln. That means for all epsilon, so if I feed it epsilon, Why can't I feed it epsilon? I can. So I don't know why this isn't working. I can feed it epsilon over 4, and that'll work. And how about by bound? And that will work. Yeah, that's what I want. I want a k so that the order k Riemann sum is within epsilon over 4. I don't know what's going on. Okay, so choose k1.
Oh, is it N now?
That's what I was trying. Oh, yes. There's no by bound here. Ay. Using. Okay, good. Okay, so K1 is how far we have to go for this to be within epsilon over 4. And then we'll choose a K2. Choose K2, HK2, using HF int M epsilon over 4. And also by bound. All right, and we may as well take the same K so that we don't have to do any funny business comparing F to itself. So let K colon equals K1 plus K2. And now what I want to say is this LM minus LN is a difference of all of these things. Let me specialize things first. So let's specialize HK1 to capital K. Specialize HK1 to capital K, and then the fact that capital K is at least the sum is by bound. So this says the order K Riemann sum of Fn differs from Ln by epsilon over 4. Excellent. Exactly what I want. And I'll do the same thing up here. Specialize HK2 with the same K. Beautiful. Then I want two different versions of Hn, one with little n and one with little m. And for that value of K, that's giving me this difference. Okay, so have H diff 1 is, what was it called again? H capital N with little n by bound. Oh, come on. Oh, colon equals. And then with what value of capital K? How about capital K? Okay, so HD1 is that the Riemann sum of order K of Fn differs from the Riemann sum of order K of capital F by epsilon over 4. So that's this distance. You see, you can check off on your diagram which things you've bound and which ones you haven't. And then let's do the same thing. So HD2 is this with an M and the same K. All right, that's that difference. So now I think I have all four differences. And here they are. HK1 is over here, then HD1, then HD2, and HK2. And now I'll just do a stupid little, can I please? Can I? Okay, now I think I can go. No, I still can't change the mode. Go away. I still can't change the mode because I'm inside a have. Again, future versions of the game will make this possible. So have bound is that L, what is it? LM? LM minus LN is less than or equal to a sum of four things. So first we have, how about FM ABNK minus LM? So I'm just going to grab this. I'm going to add and subtract this at order K. This is by sorry. Okay, can I slide this over? We don't need the picture anymore. Oh no, reload. Okay. Of course, this isn't true. What's the matter? Riemann sum. Thank you. Okay, so that's the first term. The next term is the same thing, but with plus the same thing, but with n's. Okay, so far what I've done is I've added the Riemann sum for Fn, and I've added the Riemann sum for Fn. I still have Lm minus Ln. But the absolute values let me switch which one's which. Okay, but then I'm going to compare the Riemann sum of order n of, let's see, I want to get it in the right order so that Linerith will do it for me. This is exactly what I want, plus this term, plus this term, and then plus the same term, but with m's. Okay, that's it. So that should be a trivial tactic that says Lm minus Ln is I'll add the ordered k Riemann sum of Fn and subtract the ordered k Riemann sum of Fn. I'll add the order k Riemann sum of Fn. I'll subtract the Riemann sum of order k of Fn. And to both of those, I'll add the Riemann sum of order k of capital F. And now it's going to be Linnerith with bound HD1, HD2, and HK1 and HK2. Yes. And that's the half. Okay, now can I go back? Wow, it worked. Check it out. This is kind of cool. So this key thing, we sorried out. And then we have the fact that it's Cauchy, and we go into the proof of the Cauchy. So now the goal is this Cauchy. We're going into the proof of the Cauchy. Give me the epsilon. I have to give you an n. So using the key with epsilon over 4, the key differential between this is the key. This difference is the key. That's the capital N that we use. Then give me the n and the m. And now we're going to use the integrability with a k1 for little n. That's the left-hand side. Then we're going to get a k2 for the right-hand side for m. So you see the order in which we pick these? We pick little n and little m first. And for each of those separately, we get a k1 and a k2. And we just take the worst of those because there's only 2 of them. Okay. And at the end of the day, just to move things along, that Linnerith worked, and now we've proved that this thing is Cauchy. Okay, so then finally we have, let's see, choose L, please. LHL using, what is this called? It's called seq conv of is Cauchy. The sequence converges if you can prove that it is Cauchy, and I'll feed into it is cow L. Boom. We have our capital L. We have that the sequence is Cauchy, meaning that the limit of the LNs go to L. So we can use capital L, and we can simultaneously kill this thing by giving it HL. And so now all we have to prove is that the F itself has an integral that goes to the limit of the L's. Okay, so step 1 was the L's. So what we just showed, we showed that the L's, Ln, are Cauchy, and they converge to some capital F, capital L. Now we want, so part two is that the integral of capital F itself is also capital L. In other words, the Riemann sum, i.e., the Riemann sum of order K of F should be close to L. And where am I going to get that? What's my diagram for that, Sean?
Riemann sum order K of big F is close to the Riemann sum of order K of little f sub n.
Yes, as long as for any k, as long as n is large, these two are close.
And
this is going to be close to
L sub n.
Yes. That's going to be close for a different reason, because the LNs converge to L. This is also for, so we'll get an N1 here. There's a capital N1 here. There's a capital N2 here. We'll take the best of those. This will be within, how many epsilons do we need now? 1, 2, 3. So we need epsilon over 3. So this will be, this difference will be within epsilon over 3. This is the one that we don't know. So our picture is kind of sideways from the previous one. I hope you see. This difference will make it less than epsilon over 3 by choosing n large enough relative to n2. This thing will be less than epsilon over 3, but by choosing n relative to n1. So there's 2 different reasons that this thing converges to that, and that thing converges to that. And then why are these 2 close? We take k large enough. Exactly. Now we choose k large to make this less than epsilon over 3. And that'll give us that the order K Riemann sums for capital F converge to L. All right. Let me just show you what the last level would have been. We're of course out of time. I hope you see that you can finish these levels by yourselves, and all the pieces are there. The very last level would have been the biggest boss of all, the intermediate value theorem, the thing that was completely obvious to everyone before we started this whole business, and now we have to like justify why it's actually true. So let's just talk in words. Why is this true? So I have a continuous function from a to b. At f of a, it's less than 0. At f of b, it's greater than 0. Why is there some point in between a and b so that f of c is exactly equal to 0? We finally have the tools to answer complete trivialities like this that it turns out are not trivialities at all. So final theorem. So you have a function. At a, it's negative. At b, it's positive. It's continuous. I claim there exists a c so that the function is exactly equal to 0, which is not true in the rationals. That was the last thing I owed you. How do you prove something like this? A sketch of the proof. I guess I'll just tell you since we are at negative 2 minutes. So look at the set of values. This is the set of t in a to b such that f of t is negative. Is S non-empty? What does it contain? A. Is S bounded? Yes, by B, by B itself. This is the set of real values. So the set S is this. This is S. What do we know about non-empty bounded sets? They have a least upper bound. So there exists a least upper bound for S. And my claim is that C is equal to this least upper bound. So if f of c is negative, if f of c happens to be negative, then it's not an upper bound because you can go by the continuity. If it's negative, then a little bit to the right, it's still negative. So it's not a least upper bound. If it's positive, so it's not an upper bound. If it's positive, it's not a least upper bound. By continuity, you can go a little bit further down. Okay, I'll let you fill in those details. So it is a least upper bound. And then my next claim, my next claim is that f of c actually is 0. Again, if it was positive, it wouldn't be a least upper bound. If it was negative, it wouldn't be a least upper bound. So now you have all the tools to prove trivial things like the intermediate value theorem, and non-trivial things like when integrals and limits can be interchanged. Thank you very much. It's been a pleasure.